Hey everyone, it's MJ and welcome to this video on regression. Now I'm very excited about regression because we're going to see that this is one of the most powerful subjects in the world. And I want this video to be the video on the internet when it comes to regression. So we are going to explain everything. So because it's going to be a long video, we might as well give a nice introduction on why this is so awesome. What we know from statistics is that the purpose of statistics is that we want to take data and we want to turn it into information. We've also looked at something called hypothesis testing, and we see that that's where we make some presumptions and we then go and look for some data to provide evidence. And for a lot of us, this is statistics to us. This is the subject. We use this in science to make observations and to progress with research and all of those type of things. But there is another part of stats, or another extension of it, and that is something known as regression. And regression is so powerful because it allows us to take information and find knowledge. And this is very much a game changer. What we're going to see is many jobs pay big money for people who have the skill. What you can do with regression, it's going to help you to optimize and it's going to help you to make predictions. So you can almost make the best decision and see what the future is going to hold. And both of these things are critical when it comes to achieving our goals. So, like I said, this is a powerful subject. I think it's very important that the theory is out there. So what I'm going to be doing in this video is I'm going to be focusing on the ideas behind regression. I want you guys to understand what the subject is all about, what that means, and because, like I said, this video is going to be long on its own, I am going to be skipping a lot of the maths. So I will give you hints and I will be using maths, but the actual proofs and all these other things I'm rather going to just leave out so we can rather focus on the ideas behind it, and also because computers today are doing all of the maths for us. What I will be doing is relying a little bit on statistical knowledge, and I am assuming that you guys, by watching this video, you have got some sort of background in stats. If not, I do have that whole Teachable account, which these videos will also be on. So if you want the videos in a more condensed format, that's where you can find them on Teachable. And link's going to be in the description below. But this is going to also contain all the previous videos on stats that you need as your background theory to understand. What we are going to be doing in this regression fully explained is we are going to be looking at 9 parts. So this video is going to be divided into 9 parts. Part number 1, we're going to be looking at something called correlation. Part 2, we are going to be looking at sample correlation. If we look at part number 3, we're going to get stuck into the actual linear regression model. Make sure you don't just skip ahead to that because, I mean, you do need to understand what correlation is before you can get to that. In part 4, we are going to measure the goodness of fit. And this is going to be one of the few things that we do to check how good the model actually is. Part 5, we're going to be looking more at this thing known as the slope parameter, which is given by the symbol of beta. Number 6 is where things do get a lot of fun. We're going to be looking at how to make predictions, and especially looking at the mean response and the individual response variable. Part 7, it's going to be another test to see how good our model is. We are going to be analyzing the residuals. So residual analysis will be part 7. Part 8 is where maths does get a little bit insane, and it's where you do need to be a little bit of a genius behind this stuff. But we're going to be just having a very brief introduction to what is transformation. And then, of course, this is where computers come in at part 9, where we start looking at multiple linear regression. And what we're going to see is that this stuff can get insane. It can be very complicated, and you can build an entire career from this stuff. But what we're going to be doing in this video, or in these 9 parts, is just giving you the foundation so that after you've got this, you can then go on and do weird and wonderful things. I mean, just an example of some of the things that you can do after going through this course. You can use it to make predictions around, what the Bitcoin price is going to be tomorrow. It could help you find that model. Or you might not be into making money and all of those things. You might be more into the optimization side, and you can maybe even use this. If you do go-karting like myself, you can use regression modeling to optimize what is the best strategy for your kart in order to help you win races. So there's a whole bunch of things that you can do with this skill, and that's why I think it's really important that it's out there on the internet so that people can embrace it. But without further ado, let's jump on to part 1. So yeah, part one. What we're going to be doing is, after each of the parts, you can have a little bit of a break, or you can just keep watching them in its entirety. But yeah, part 1, we're going to be looking at this idea of correlation. What do we mean by correlation? Correlation essentially means the strength and direction of a relationship. So we're looking at the strength and direction of a relationship. So what does that mean? What I'm going to do is I'm going to draw out 5 different graphs. So these are our X and Y axes here. What we might have is, let's say, these are all of our points. Remember, this is the X and this is the Y. If those are all of our points and it's just all random, scattered about, we will say that this is uncorrelated. If we can see some sort of pattern where as X increases, Y increases, we will say that we have a weak positive relationship. We can maybe even see that this gets a little bit stronger, and then we're going to use the terminology of this is strong positive. If it follows a perfect little linear line like that, we are going to say that it is perfect and positive. But remember, we can also get it, if the data starts doing this, we can see that we have, this is perfect negative. And I mean, you might be saying, okay, hold on, what is this Y and what is this X? Y, I mean, could be the interest. Oh, no, what we would have for Y? Y would be the Bitcoin price, say the Bitcoin price. And X could be the interest rates. Or if we're talking karting, Y could be our lap time and X could be our weight. And what we could see in this situation, we could see something like a negative correlated thing where as our weight increases, weight in this will be positive because as our weight increases, our lap time will also increase. We could see a negative correlation with Bitcoin and interest rates as an example of a negative correlation. So that's what we kind of have. But that's all good in theory. Where do we get these numbers from? And I mean, we can't just say something is strong correlated. We need to have some sort of numbers to help us in this thing. So what we've had, if we look back in the beginning of stats, we looked at this thing known as the variance. And the variance is simply how spread out a random variable is. So how spread out a random variable is. We then also looked at something called covariance. And this is the joint spread of 2 random variables. And covariance is kind of what we're after. We want to see what is the spread between our Y and our X? How are they spread out? The thing about covariance is that it's a bit of a meaningless number, because what do we mean if our covariance is 10, or what do we mean if our covariance is 100? It's a very difficult number to compare. And that's where correlation comes in. Correlation, which is denoted by the symbol P, or written like this, cor x and y, it is equal to the following formula. We have the covariance of x and y, but what we're doing is we're dividing it by the variance of x and the variance of y. And what this is going to do, it's going to remove that whole magnitude or distortion that would have come from the data, and it's going to allow us to compare correlations across various data sets. Because what this does is it's going to make a set of bounds for our correlation. So our correlation can never be greater than 1, and it can be never be less than -1. Now, why are we so interested in correlation when it comes to regression analysis is that if our correlation is equal to 0, then it means that x and y are uncorrelated and that it's pretty pointless to do regression. If we see that the interest rate and the Bitcoin price are uncorrelated, then there's no point in building a model with interest rate as our explanatory variable and Bitcoin as our response variable, because it's going to just be an absolute waste of time. So this is what we want to do, is before we go ahead and do our regression analysis, we check the correlation, because if the correlation is 0, then like I said, there's no point in wasting our time. The problem though, the problem is that this is the population correlation, and very rarely will we have access to the population data. Instead, we're going to have access to the sample data, and that's where part 2 comes in. So let's move on to part 2 of regression. And in part 2, we're going to be looking at something called the sample correlation. And the reason why we have to look at the sample correlation is because the population correlation is sometimes beyond us, or we don't have access to all of it. We do sometimes have access to a sample, and we now need to use our sample to come up with an expectation or a guess for what the population correlation is supposed to be. So let's look at sample correlation. What is it? It's denoted by the little letter R, and it is equal to SXY divided by SXX SYY. Now, let's just explain what these SXY things actually are. And it's important because we're going to be using these formulas throughout the rest of the course. So it's important that you pay attention to what these things are. SXY is equal to the sum of the xi minus x bar, yi minus y bar. Okay, almost think of it as very much the covariance of x and y. SYY is going to be equal to the following: the sum of yi minus y bar squared, and the same here, we're going to have xi minus x bar squared. And you can see it's similar to this whole concept. Oops, I have made a terrible mistake. The variance of the y's and the variance of the x. Okay, and you can see this formula over here looks like that formula over there, but remember, we are using, this is in a sense using sample data, whereas this stuff over here was using population data. Okay, like I said, go check out the Teachable course where we explain what sample and population is in some of the earliest background stuff on stats. But I think we should all be happy with that. What we now see is that because R is a function of the sample data, what that means is that R is going to be a random variable. So because R is a random variable, we can do a whole bunch of lovely things on it. But what it also means is, as a random variable, we could have a situation where our population correlation is equal to 0, but due to the fact that it's a random variable, the sample might not be equal to 0 due to random fluctuations, which means we do need to do a bit of a hypothesis test. And the hypothesis test will be something as follows. We would have HO, population correlation, is equal to 0, and H1, alternative hypothesis, that it is not equal to 0. We then have the following as our test stat, which is as follows: 1 minus r squared, and this is with the t distribution. Like I said, I do want to skip the maths, but if you want to prove this for yourself, I mean, you do need to rely a little bit on the central limit theorem, and look at the situations where your sigma squared is unknown. But like I said, the maths behind this can make an entire video just on that. But just take it as a result, take it as one of the results in this course, and we're going to see that if we have this as our test stat, we can then calculate our confidence intervals at 95%. That's going to give us two numbers, and what we know is that if 0 is not included in this confidence interval, then we can reject H0, and we can continue with our regression model. So just a little bit of a recap. Why are we doing everything that we're doing? Before we go into linear regression models, we want to just check to see if there is some sort of relationship between the data. In order to test what the relationship is, we're going to need this thing known as the correlation. And the correlation is the covariance between the two data sets divided by the variance of each one. However, we might not be able to have access to the population data, in which case we need to take a sample. From the sample, we can calculate the sample correlation, and then we can do a hypothesis test to see if it isn't, or if 0 is not a 95% possible in the confidence interval. Once we have all of that, we can now go on to part 3, where we're going to be looking at linear regression models. Okay, so now we're coming up to part 3. So yeah, just a bit of a recap. Before we look into our linear regression models, we had to look at the correlation to see if it's actually worth doing. We want to make sure that the data is not uncorrelated, but of course that's for the population. We might not have access to the population data, so we're going to look at the sample correlation, which is a random variable, which means we have to do a hypothesis test around it to make sure that we can do the linear regression. Okay, so that is a bit of like the backstory. Now we're actually getting into the whole thing, because yeah, once we know that our correlation or sample correlation is not equal to 0 with a 95% confidence, we can fit our model. Now this becomes a whole thing. You know, what type of model do we fit? And when you have this as your day job, when you're a data scientist and you're doing this will take up a big chunk of the process, is to decide what model are we going to use. For now, what we're going to be doing is we're going to be using the baby model, which is known as the linear model. We're just going to be using this. It's the simplest, and what this is going to do, we're going to build a lot of the theory or talk about a lot of the ideas, which can then extend to the other models that you might have chosen. The linear model, in its very raw sense, is something like this. If we have our data, we've tested that there is some sort of correlation, we're then going to draw a straight line, and that is our linear model. So if we were to write it out mathematically, we would have the following. We'd have yi is equal to alpha plus beta xi plus ei. And I think what we're going to do is just quickly explain what each of these things are. So this guy over here is our response variable. We then have our alpha, which is our intercept parameter. Beta is going to be our slope parameter, xi is going to be our explanatory variable, and then ei is going to be our error variable. And a little fun thing with the error variable is that it is distributed normally with 0 and another parameter called sigma squared. And what this means is that in order to build our model, so in order to build our linear regression model, we have some parameters that we need to estimate. And these parameters are alpha, beta, and sigma squared. Now, once we find what these three parameters are, the whole process of that is known as fitting the model. So what we're going to be doing now is we're going to be looking at how do we actually fit the model. And so yeah, let's end off this part by looking at that. We've got the estimate for the slope parameter, and it is equal to sxy divided by sxx. The estimate for the intercept parameter alpha is equal to y bar minus beta hat x bar, which is the estimator of the slope parameter, and then we have sigma squared hat is equal to 1 over n minus 2 sigma, or the sum of yi minus yi hat squared. Okay, now if you're probably thinking, where on earth did we get these things from? Essentially, the mathematics behind it is we're doing a simultaneous equation. The one equation is the sum of the yi's is equal to alpha n plus beta sum xi, and then we also have the following one as well. And what we do is, yeah, simultaneous equations. We do the maths. It's not that difficult, but it takes up a bit of time, and we get those two guys over there. We're not going to be going into that result as well. Like I said, we just want to stay away from the maths and focus on the ideas. But what we will start to see is that these things, once again, are random variables. So we're going to see that our little b hat guy over here is a random variable. It's going to have an expected value, which is going to just equal this, shows that it's unbiased. And we're going to have the variance of it, which is an important result, which we're going to be using a lot later on, as follows. One thing to always keep in mind is that the fitted model will always go through the point x bar, y bar. It's one of the little quirks of linear regression models. Anyway, that concludes part 3, which is just an introduction to fitting the model. Okay, let's look now at part 4. What we're going to be doing in part 4 is we want to measure the goodness of fit. Okay, and what do I mean by the goodness of fit? Well, let's just draw it out to illustrate what I mean. We might have two linear models like this, but the one might have all the data points very close to it. We could say that's quite a good fit. Whereas we could have another one that looks like this. And you can see number A has got a much better fit than number B. However, we don't want to just rely on our own eyes. We want to actually have some mathematics behind it, or a number to actually state how good of a fit it is. Another way of saying it is how much is explained by the model. So what we mean by that is, in scenario A, a lot is explained by the model, and in B, not a lot is explained by the model. So what we need to be doing here is we need to therefore study this SYY in more detail, which, as we remembered, is equal to the sum of the YI's minus the Y bars squared. And if we remember from the previous part, we have our linear regression model as follows. We have yi is equal to alpha plus beta xi plus ei, And we're going to see that there are two sources where we're getting the yi's from. Okay, this source over here, it's the xi's. Okay, and this we could say is the good source, and then we have the ei's, which I guess you could say is the bad source. So what we can do is the following. Okay. The next little thing here is a bit of a jump in mathematics. So once again, it's one of these results that we're just going to accept, but you can look into it a little bit more. We have this yi, so if we look here, we have yi minus y bar. And we can say that this is equal to yi minus yi hat. And whatever we subtract, we also have to add. So you can see those two terms cancel each other out with y bar there. But what we're going to see, and we're not going to prove this, it's quite a magical result, but we get the following. When we sum this side and we square it, something interesting happens in the sense that we can also do the same on this side. Okay, now this doesn't happen for all cases. This is a special case that this happens for. The reason being, or if you do want to try and prove that that is the situation, I will give you a hint, and the hint is that the b hat is equal to sxy divided by sx. Remember, we looked at that in part 4, or in the earlier part, and you do need that relation in order to prove the following. But what this does is it partitions the response of the model. So what we're going to see is we can call this over here, this is that SYY. We can also call it the total sum of squares, and we use this as the symbol for that. So we can have this as the total sum of squares. But what we've also done is we've broken it into this thing over here, which we're going to see a lot later is your EI. Your EI is equal to your YI minus your YI hat. So this is the residual sum of estimated errors, or SS res. Res is short for residuals. Plus what we have over here, which is our regression sum of squares. So plus SS reg. And it's a little bit unfortunate we've got res and reg. They look a little bit similar. But essentially what we're doing here is we're taking the variance and we're splitting it up into these two components. This component over here, which is represented by the EIs, or the unexplained part of the model. And we have SS reg, which is XI, which is how much is explained by the model. So we want majority of SS tot to come from SS reg, and we want SS res to be as small as possible. Now when we start getting to a little bit of the maths, we can see that the estimator for this is also equal to SS res divided by n minus 2, and we can see that SS res itself is equal to SYY minus SXY squared over SXX. Now this is where the maths does get a little bit tricky, and in the exam they can ask you to use these puzzle pieces to solve certain problems. So it is important that you go through this yourself and you just get a better understanding. But what is cool is, I mean, these things as well, you can take the expected value. So the expected value of SS total, which is the total sum of squares, it is equal to n minus 1 sigma squared plus beta squared SXX. The expected value of SS reg is going to be equal to sigma squared plus beta squared SXX. And like I said, we're not going to be going into the actual proofs for these things, but you can do them yourselves if you want to, if you just want to double check. But essentially what we are saying is a good fit, we're saying that the model is a good fit if our SS reg, which is, remember, the X or the explained, is high, and our SS res, the residuals, is low. And remember, that's given by the error term. What we can also do is we can explain this in a nice way with something called the coefficient of determination. Coefficient of determination. And that's given by capital R squared, which is equal to SS reg divided by SS tot. Basically, we want to see how much of the variance is a proportion of the total, which is also given by this formula here. You can see how useful knowing those SXXs and SYYs actually are, because that's an alternative formula. But essentially, your coefficient of determination, we're going to quote it as a percentage, and it can be either between 0% and 100%. What is interesting is if we look at it like this, if we look at that formula there, and we compare it to our sample correlation, it's very interesting how it is the square of the sample correlation. And this makes sense. If we have a very strong correlation, we're expecting our linear model to be able to explain a lot of it. If our sample correlation is very weak, then we're expecting our model not to be able to explain a lot of it. So it is very interesting to see how these two things are connected. Okay, now we are moving on to what part is this? This is the slope parameter, which is part number 5. Okay, so let's get into this part number 5, and we're going to be looking at the slope parameter in a little bit more detail. Okay. But now, in order to understand the slope parameter, we just need to make a few assumptions about our error term. And our little errors, what we're going to be assuming is that they are all independent of one another, and we're going to be assuming that they are normally distributed. Okay. Now, what is interesting is when we assume this, we can say the following. We can say that following that our response variable is going to be normally distributed with alpha plus beta xi and sigma squared as the variance. Of course, this is the beta one that we're interested in, and we're going to see that it itself is normally distributed with beta and sigma squared sxx. Okay. In order to do anything more, we do need following results. Okay, and again, we're not going to be proving these results, but the results are, one, that the estimate for our slope parameter and sigma squared are independent. Okay, and 2, we're going to be saying that n minus 2, the estimator for the variance divided by sigma squared, is distributed according to the chi-squared distribution of n minus 2. And again, this is something that you should be comfortable with if you've been doing the previous courses. Otherwise, go check out those videos if you're like, whoa, what on earth is sigma squared? Where did that come from? Anyway, we're going to say that this thing is equal to n. And once we have all of this, I mean, the maths is a little bit tricky, but we can derive the maximum likelihood estimators of alpha, beta, and sigma squared, and that might very well be an exam question, especially if you're studying actuarial science. So you do want to make sure that you're comfortable with that maths. But because of the fact that we've got the maximum likelihood estimators of these guys, we know then that the following is true of our slope parameter, that we can put it in this format over here, and we have it as in the standard normal. And let's call this result equal to m. Now, Since these two things are independent, okay, what we can do, and from the central limit theorem and all of our understanding of probability distributions, we're going to see the following. Okay, we've got this as our t distribution with n minus 2 degrees of freedom. Now, what that basically allows us to do is write our slope parameter in the following way. And you might be saying, hold on, what is that SE thing? What is this? This is almost the estimated standard error or the standard deviation kind of idea, where we have it like this. Okay, we're using the estimator over here instead of the actual population parameter. And the whole idea here is that we're going to use the standard normal when sigma is known, but very likely that it's unknown, in which case, according to the central limit theory, we can use the following here when this is unknown. Okay, and this is great because now it's going to let us use this as our test statistic when it comes to calculating confidence intervals and hypotheses. I mean, we could very much get to a stage as our confidence interval as something like this, plus minus t alpha divided by 2 n minus 2 times SE beta hash. And bam, we have our confidence interval. What is interesting is, once again, if we look at it a little bit closer, we will see the following. We see that beta hat is equal to this, and R is equal to this over here, our sample correlation. And what this basically means is that if beta hat is equal to 0, then the only way that can equal to 0 is if SXY is equal to 0, and if XY is equal to 0, then R has to be equal to 0. And what we're seeing here is that if our slope is 0, then it means that the data is uncorrelated. So this is useful if we want to check if the model is a good fit. But why it is a little bit more superior to the sample correlation is because now we can start testing null hypothesis where, say, beta is equal to 1, or where beta is equal to 2 or 3 or 4. It can extend our testing abilities. Okay, let's use orange for the next part. I think this is part 6. I haven't been keeping count. Yeah. Okay, this is part 6 where things start getting very interesting. We're going to be looking at the mean response and predictions of individual responses. And I guess this is the whole point of regression analysis. You know, what is yi going to be when we have xi? And what we can, I think, yeah, maybe let's just explain this right at the get-go, is let's say I'm busy doing karting. Now in karting, I can do a 1 lap for qualifying, and I can do 15 laps for the race. Okay, when we're looking at the average lap time of the race, we're going to be using the following mean, and when we're just going to be looking at 1 lap on its own, we're going to be using YO. Okay, so I think that is just a very important that we get that out of the way, just in case you get a little bit confused, like you're saying, where on earth is this mu0 thing coming from? It is the mean response of y given xo, and I mean, once again, we're seeing alpha plus beta xo. Big thing to notice is there are no EIs in this formula here because it is the mean response, which means we can estimate the mean response with our intercept parameter and our slope parameter given what our xo is. Now it's important to remember that this, though, is still a random variable, and we're going to have the following set of results. Okay, the first result should not scare anyone because it's unbiased. The second result is where things get a little bit interesting. If we have to take the variance of this estimator, we're going to get an interesting formula. Let me just write it out. Okay, now if you want to prove this, if you want to be very brave and prove this, I'll give you two hints. Okay, the one hint is that the variance of alpha, or the intercept parameter, is equal to the following. And two, that the covariance of alpha hat and beta hat is equal to negative x bar. Now, you need these two results if you are going to prove this, but if in an exam or in some unfortunate situation you are told to prove this, you can't just state these results. You're going to have to do two mini proofs for each of them as well before you can just state them. So like I said, this is where the maths can get a little bit insane. But yeah, the important thing to realize is that is the result. And just like how we did above, we can take the standard error of it. The important thing to note here is not only are we taking the square root of it, okay, but watch, there is another big difference. There's another big difference. Feels like that game Spot the Difference. But what we're going to be seeing here is this. And there you can see it. We're using the estimator of sigma, as this is the situation where the population variance is unknown. But what is nice is it means, oh, look at this, we get a lovely little test stat as the following. And it is according to the t distribution with n minus 2, which once again we can use for confidence intervals and the null hypothesis. But that's all good for the mean response. What if we want to do it for an individual response? So, like I said, this was the way to think about it when we're doing my average lap time over the race of 15 laps. What happens if we want to look at qualifying where it's just one lap? We're only getting one chance. What happens then? So in this case, we are going to use YO hat, and at first it looks very similar to what we had before. I mean, look that's actually the same. However, so the expected value is going to be the same. But what about the variance? The variance is, and I think just let's think about it logically, okay? If you do something 15 times or if you do something once, what is going to be more variable? And the answer is when you only do it once, because you don't have the multiple things canceling each other out or tending towards something. So how do we handle the extra variance? And what we do is, to handle the extra variance, we're going to add in another sigma squared, which means the variance for y hat 0, 0 is equal to the following. 1 plus 1 over n plus xo minus x bar squared divided by xx sigma squared. Okay, you can see we've added in another one of these things to compensate for the fact that the variance should be bigger. But I mean, once again, we then just get to the situation where, I mean, now you should start seeing the pattern, start seeing that the stuff actually isn't that difficult, because once again, we have it like this. We're using the estimator, and we can use this as our test stat in order to do our confidence intervals or our hypothesis testing, which is very nice, very, very nice. Yeah, so that was part 6. When we come now to part 7, what we're going to be doing is checking the model. So checking the model. What do we mean by that? Well, checking the model means we're going to be observing something known as scatter plots of the residuals. Now, you might be saying, okay, hold on, what is a residual? Well, the residual at xi is ei hat, which is equal to yi minus yi hat. Okay. And the reason why we want to check the model, or we want to observe these scatter plots, is for 2 reasons. One, we want to check our assumptions. Do we have true errors in our model? Are our little e's identical and independently distributed around the normal with a mean of 0 and a variance of sigma squared? And 2, what we want to do is we want to investigate the nature of the relationship between our response and exploratory variable. So in a perfect situation, our scatter plot would be just a random scatter, and we can be like, okay, fantastic, fantastic. That is what we want. We can then be quite happy with the model. However, let's say we have a straight line and the data does this. Okay, it's almost got a bit of a exponential growth, and we fitted a linear model. What we can then expect is our random errors are going to be growing as time goes on. You can see they're getting worse and worse. The model starts deteriorating as we extend it, and we don't want that. We want our model to be the same whether we're in the beginning or at the end. What this shows is we now have a pattern forming in our residuals, and this is panic mode. So we're like, no, we don't want patterns in our residuals. This is very bad, and it's going to show that our model is inadequate. Okay, if there's patterns in the residuals. However, there is a way to deal with our patterns if the residual is not doing well, and that's what we're going to be looking into here in part 8. So part 8, we're going to just briefly talk about something called transformation. Okay, and transformation, it's something like, as we said, when we have a pattern in our residual analysis. So we might have a situation where, like I said, we have a growth model. So an exponential growth, which means as soon as we fit a linear regression, the errors are going to be increasing as time goes forward. So how we would show this is that the expected value of our response variable given our explanatory variable is equal to alpha to the power of beta xi. Now, what do we do? Because we need something in a linear format if we're going to be doing a lot of our testing. Fortunately, we can use a mathematical concept known as transformation, and this is the transformation. We can set up a new variable, which is a transformation of our response variable. And if we look at it now, we will see that wi is going to be equal to log alpha plus, because if you understand how logs work, we now get this situation here, which is our linear model. So we have transformed an exponential into a linear, which is going to be lovely because it's going to allow us to do all of our wonderful tests. Although one thing you've noticed is I've added the error term. Okay, now this is implying that the error structure is additive, which means it was multiplicative in this situation over here. But there's potential problems with this, and I mean, I'm getting down a little bit down the rabbit hole. which is something we look at more in generalized linear models, which is a much later actuarial exam. So I just wanted to briefly mention transformation to you. It is something that you'll deal with in the future, and it is where things do get a little bit tricky. But I do want to end off with the subject on regression with part 9, which is where we're looking at something called multiple linear regression models. And I think this is where the real fun actually begins, because what we're going to be doing here is we're going to be looking at more than one variable. So if it's Bitcoin, we might want to look at interest rates, and we might also want to look at USD debt, and we might want to look at, I don't know, inflation. We might even want to look at trading volumes, etc., etc., etc. When it comes to karting, we might want to look at, say, okay, not only what is the weight of the cart, but what is the tire pressure, as well as, what are the track conditions as well. We can start getting more than one variable. And the idea behind this is that more information means that our prediction power is going to be more accurate. Okay, predictions are going to become more accurate. Okay, so we want it. How does this look mathematically? Well, we have it of the following form: y given x1, x2, all the way, up to xk, it's going to equal to, we're always going to have just one intercept parameter, but look at this. We now are going to have a whole bunch of these b's, which we call the multiple regression coefficients. So once again, this y here is a random variable, and all these b's are what we call the multiple regression coefficients. So how we would then write it out is the following: yi is equal to alpha plus b1 x1 plus dot 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 plus bk xk plus our little error term. But like I said, this is very much just the tip of the iceberg. We can start playing around with many different models. Sometimes we can combine variables, and the maths does start getting a little bit heavy. And so this is where computers are used. But yeah, I thought I'd just give you a very brief introduction on multiple linear models. So yeah, if you've made it this far, welcome. Well done. You've made it to the conclusion. Look, in this video, we did talk a lot about confidence intervals, hypothesis testing, things known as test stats, estimators, etc., and etc., etc. So if you're new to data science and you've done this video and you're like, what on earth was he talking about? I do have a course on Teachable. There's actually a few other videos I do have on this channel as well, but majority of them are going to be on Teachable with some exam help and some other goodies to help you really understand these concepts. And like I said, the link is going to be in the description below, and you can follow that. And also feel free to ask me questions on this platform. All the videos are nicely put together, so it just makes for a much better learning environment. Anyway, hope you guys enjoyed this course on regression analysis. And yeah, the maths is a little bit intimidating, but I hope we were able to communicate the big ideas, and we can see what a powerful form of stats this is. As always, thanks so much for watching. Cheers.